Deep in the vast expanse of the universe, where stars are born and galaxies collide, lies a cosmic spectacle unlike any other. Meet the MICE galaxies, officially known as NGC 4676, a pair of colliding galaxies locked in a gravitational dance that has been unfolding for millions of years. But this isn't just a story of two galaxies merging. Hidden within their swirling arms and glowing cores are some of the strangest, most mysterious objects ever observed in the cosmos. From ghostly nebulae to twin black holes on a collision course, the MICE galaxies are a treasure trove of cosmic oddities that challenge everything we think we know about the universe. In this video, we're diving into the heart of this galactic collision to uncover 50 bizarre objects that defy explanation. Each one tells a story of chaos, creation, and mystery, offering us a glimpse into the incredible forces shaping our universe. What secrets do these galaxies hold? What strange phenomena are waiting to be discovered? And how do these objects reshape our understanding of space itself? Stick around, because by the end of this journey, you'll not only witness some of the most extraordinary sights in the cosmos, but also gain a deeper appreciation for the wonders that lie beyond our world. The universe is full of surprises, and the MICE galaxies are here to prove it. Let's begin. Now, let's zoom into the heart of the MICE galaxies, where one of the most astonishing discoveries awaits. At the very core of this cosmic collision, astronomers have uncovered not one, but two supermassive black holes, each with a gravitational pull so immense that not even light can escape. These twin black holes are the result of the galaxy's ongoing merger, a process that has brought their centers closer together over millions of years. But how were these colossal objects detected? Scientists used a combination of advanced telescopes and gravitational wave observations to pinpoint their presence. Gravitational waves, ripples in the fabric of space-time caused by massive objects in motion, provided crucial clues. These waves, first predicted by Albert Einstein, allowed researchers to listen to the universe in a whole new way, revealing the presence of these black holes as they spiraled closer together. The implications of their eventual collision are nothing short of extraordinary. When these two black holes finally merge, they will release an enormous burst of gravitational waves, sending shockwaves through the cosmos. This event will not only reshape the structure of the MICE galaxies, but also provide scientists with invaluable data about the nature of black holes and the forces that govern our universe. What makes this discovery even more fascinating is the role it plays in our understanding of galactic evolution. The twin black holes are a testament to the chaotic and dynamic processes that occur when galaxies collide. As they continue their gravitational dance, they offer us a front-row seat to one of the most dramatic events in the universe. Next, we'll explore another mysterious feature of the MICE galaxies, a glowing cosmic ribbon that stretches across the collision zone, defying our expectations of what galactic interactions should look like. Now, shifting our gaze to another marvel within the MICE galaxies, we encounter a breathtaking structure that seems almost otherworldly, a massive, glowing ribbon stretching across the collision zone. This cosmic ribbon, with its ethereal glow and intricate patterns, is one of the most striking features of these merging galaxies. But what exactly is this luminous phenomenon, and how did it come to be? Astronomers have proposed several theories to explain the origin of this extraordinary structure. One leading idea suggests that the ribbon was formed by shockwaves generated during the collision of the two galaxies. As these galaxies crash into each other, immense forces are unleashed, compressing gas and dust and creating ripples that stretch across vast distances. These shockwaves could have triggered the formation of the ribbon, illuminating it with the energy released during the collision. Another intriguing possibility is that magnetic fields play a significant role in shaping this glowing structure. Magnetic fields, which are present throughout galaxies, can influence the movement of charged particles, guiding them into intricate patterns. In the case of the MICE galaxies, these magnetic fields might have sculpted the ribbon, giving it its unique, flowing appearance. This interplay between magnetic forces and the chaotic energy of the collision could explain why the ribbon looks so different from anything else observed in the universe. What makes the cosmic ribbon truly remarkable is how it challenges our understanding of galactic interactions. Typically, when galaxies collide, we expect to see chaotic, irregular structures. Yet here, we have a ribbon that appears almost delicate and symmetrical, defying expectations. Its presence suggests that even in the midst of cosmic chaos, there can be moments of unexpected beauty and order. As we continue to study this glowing ribbon, it offers us a glimpse into the complex processes that shape the universe. It reminds us that even in the vastness of space, there are still mysteries waiting to be unraveled. Next, we'll turn our attention to another enigmatic feature of the MICE galaxies, a ghostly nebula that seems to float between the colliding galaxies, adding yet another layer of intrigue to this cosmic drama. Now, as we venture deeper into the mysteries of the MICE galaxies, our attention is drawn to a hauntingly beautiful sight, a faint, ghostly nebula that seems to drift between the two colliding galaxies. This ethereal cloud of gas and dust glowing faintly against the backdrop of space adds an almost spectral quality to the cosmic drama unfolding here. But what is this ghostly nebula, and how did it come to exist in this chaotic environment? Astronomers believe this nebula may have formed from material ejected during the violent collision of the two galaxies. As the galaxies interact, their immense gravitational forces can fling gas and dust outward, creating vast clouds that linger in the space between them. Over time, these clouds can cool and condense, forming structures like the ghostly nebula we see today. Its faint glow is likely the result of starlight reflecting off the dust particles or the ionization of gas by nearby stars, giving it an eerie, otherworldly appearance. What makes this nebula particularly fascinating is the possibility that it could be a cradle for new star formation. Within its wispy tendrils, pockets of gas and dust may collapse under their own gravity, igniting the birth of new stars. If this is the case, the ghostly nebula could be a hidden nursery, quietly nurturing the next generation of stars even as the galaxies around it continue their tumultuous dance. This potential for star formation adds another layer of intrigue to the nebula, transforming it from a mere remnant of the collision into a dynamic and evolving structure. The presence of this ghostly nebula also raises questions about the broader impact of galactic collisions. While such events are often thought of as destructive, they can also be creative forces, scattering material across vast distances and setting the stage for new cosmic phenomena. This nebula serves as a reminder that even in the chaos of colliding galaxies, there is beauty and potential for renewal. As we marvel at this ghostly nebula, we are reminded once again of the complexity and wonder of the universe. Next, we'll turn our gaze to another strange object within the MICE galaxies, a peculiar spiral-shaped anomaly that challenges our understanding of galactic structures. Now, shifting our focus to another enigmatic feature within the MICE galaxies, we encounter a peculiar spiral-shaped anomaly that defies conventional expectations. This strange structure, nestled within one of the galaxies, stands out with its intricate, swirling patterns that seem almost too perfect to be a product of chaos. But what exactly is this spiral anomaly, and how did it come to exist in such a turbulent environment? Astronomers are divided on its origins. One theory suggests that this spiral could be the remnant of a smaller galaxy that was absorbed during the collision. As the larger galaxy consumed its smaller companion, the gravitational forces may have stretched and twisted the smaller galaxy's material, creating this spiral-shaped relic. If this is the case, the anomaly serves as a cosmic fossil, preserving the memory of a galactic merger that occurred millions or even billions of years ago. On the other hand, some researchers propose that the spiral anomaly might be a unique structure formed directly by the collision itself. The immense tidal forces generated as the two galaxies interact could have sculpted the gas and dust into this intricate spiral pattern. This would make it a rare example of how galactic collisions can produce unexpected and beautiful formations, challenging our understanding of how such events shape the universe. The spiral anomalies' intricate patterns are not just visually stunning, they also provide valuable clues about the dynamics of galactic collisions. By studying its shape and structure, astronomers can gain insights into the forces at play during these cosmic encounters. For instance, the tightness of the spiral's arms could reveal information about the speed and angle of the collision, while the distribution of material within the spiral might hint at the conditions that led to its formation. What makes this anomaly even more fascinating is its potential to evolve over time. As the galaxies continue to interact, the spiral could be further distorted, eventually blending into the larger structure of the MICE galaxies. Alternatively, it might remain as a distinct feature, a lasting testament to the collision that created it. Either way, the spiral anomaly serves as a reminder of the complex and ever-changing nature of the universe. As we marvel at this cosmic spiral, we are left with more questions than answers. Is it a remnant of a long-lost galaxy, or a unique creation born from the chaos of collision? Whatever its origins, this spiral anomaly adds yet another layer of mystery to the MICE galaxies, inviting us to explore further and uncover the secrets it holds. Next, we'll turn our attention to a dazzling cluster of stars that shines brightly amidst the chaos, a starburst cluster that reveals the explosive potential of galactic collisions. Now, as we venture deeper into the chaos of the MICE galaxies, we encounter a breathtaking spectacle, a starburst cluster that radiates with the brilliance of countless newborn stars. This dazzling cluster, born from the fiery aftermath of the galactic collision, stands as a testament to the transformative power of such cosmic encounters. But what exactly makes this cluster so extraordinary, and how did it come to be? The collision between the two galaxies unleashed a torrent of gravitational forces, compressing vast clouds of gas and dust to unimaginable densities. This compression triggered an intense burst of star formation, igniting the birth of thousands, if not millions, of stars in a relatively short cosmic timespan. The result is a starburst cluster, a concentrated region of young, hot stars that shine with unparalleled brightness. This cluster is not just a random scattering of stars, it's a tightly packed, luminous hub that dominates its corner of the galaxy. What's truly remarkable about this starburst cluster is its sheer size and luminosity. Spanning hundreds of light years, it outshines many other regions of the MICE galaxies, making it a beacon of light amidst the chaos. The stars within the cluster are predominantly massive and short-lived, burning through their fuel at an accelerated rate. This means that, while they shine brightly now, their lives will be brief, ending in spectacular supernova explosions that will further enrich the surrounding space with heavy elements. But the story of this cluster doesn't end with its current brilliance. Over time, as the stars within it age and the cluster evolves, it has the potential to transform into a globular cluster, a dense, spherical collection of ancient stars that orbit galaxies like cosmic relics. If this happens, the starburst cluster will become a lasting legacy of the collision, a celestial time capsule that preserves the memory of this explosive event for billions of years to come. The starburst cluster also offers astronomers a unique opportunity to study the early stages of star formation on a grand scale. By observing the cluster's structure, composition, and dynamics, scientists can gain insights into the conditions that lead to such intense bursts of star birth. For instance, the distribution of stars within the cluster can reveal how gas and dust were compressed during the collision, while the presence of massive stars provides clues about the initial conditions of the star-forming clouds. As we marvel at this radiant cluster, we are reminded of the dual nature of galactic collisions, destructive yet creative, chaotic yet beautiful. The starburst cluster is a shining example of how the universe can turn destruction into creation, forging new stars and new possibilities from the wreckage of colliding galaxies. Next, we'll explore a mysterious dark vortex that lurks within the MICE galaxies, a shadowy enigma that challenges our understanding of galactic dynamics. Now, shifting our gaze to a more enigmatic feature of the MICE galaxies, we encounter the dark vortex, a shadowy, swirling phenomenon that seems to defy explanation. This mysterious structure, cloaked in darkness, stands in stark contrast to the vibrant starburst cluster we just explored. But what exactly is this dark vortex, and what secrets does it hold? The dark vortex appears as a vast, swirling void within one of the galaxies, its edges marked by faint wisps of gas and dust. Its shadowy core seems to absorb light, creating an eerie absence of brightness that draws the eye. Astronomers have proposed several theories to explain its nature. One possibility is that it's a massive dust cloud, so dense that it blocks the light from stars behind it. Another theory suggests it could be a region of intense gravitational distortion, where the fabric of space-time is warped by the immense forces at play during the galactic collision. What makes the dark vortex particularly intriguing is its swirling motion. Observations reveal that the gas and dust around its edges are caught in a slow, spiraling dance, as if being pulled inward by some unseen force. This motion has led some scientists to speculate that the vortex could be linked to the supermassive black hole at the galaxy's center, with its gravitational influence shaping the surrounding material into this swirling pattern. Alternatively, it might be the result of shock waves from the collision, creating a turbulent region where gas and dust are compressed and twisted into this dark, mesmerizing form. The dark vortex also raises questions about its role in the broader dynamics of the MICE galaxies. Could it be a temporary feature destined to dissipate as the galaxies continue to merge? Or is it a more permanent structure, one that will persist long after the collision has settled? Its presence challenges our understanding of how galactic interactions shape the distribution of matter, offering a tantalizing puzzle for astronomers to solve. As we ponder the nature of this shadowy enigma, we are reminded of the many mysteries that still lie hidden within the cosmos. The dark vortex serves as a stark reminder that even in the brightest corners of the universe, darkness can hold its own secrets. Next, we'll turn our attention to the Luminous Bridge, a glowing structure that connects the two galaxies and reveals yet another fascinating aspect of their collision. Now, as we shift our focus to another breathtaking feature of the MICE galaxies, we encounter the Luminous Bridge, a radiant arc of gas and stars that stretches between the two colliding galaxies like a cosmic highway. This glowing structure is not just a stunning visual spectacle, it's a vital clue to understanding the forces at play during this galactic collision. The Luminous Bridge was formed by the immense tidal forces generated as the two galaxies grazed past each other. These forces, akin to the gravitational pull that creates ocean tides on Earth, pulled streams of gas, dust, and stars out of the galaxies, stretching them into a luminous ribbon that now connects the two. This process is a direct result of the galaxy's gravitational interaction, showcasing how even the gentlest of cosmic encounters can leave dramatic imprints on the fabric of space. What makes the Luminous Bridge particularly fascinating is its role in transporting material between the galaxies. As the bridge glows with the light of countless stars and ionized gas, it acts as a conduit funneling matter from one galaxy to the other. This exchange of material is crucial for the evolution of both galaxies, as it can trigger new waves of star formation and even influence the growth of their central supermassive black holes. The bridge is essentially a lifeline, ensuring that the collision doesn't just destroy but also creates, reshaping the galaxies in profound ways. The Luminous Bridge also offers a unique window into the collision process itself. By studying its structure and composition, astronomers can trace the history of the interaction between the two galaxies. The bridge's glowing gas reveals the paths taken by the tidal forces, while its embedded stars provide clues about the timing and intensity of the collision. This information helps scientists piece together the sequence of events that led to the current state of the MICE galaxies, offering insights into how such collisions shaped the universe over billions of years. As we marvel at the beauty and complexity of the Luminous Bridge, we are reminded of the interconnectedness of the cosmos. This glowing structure is not just a remnant of destruction, but a testament to the creative power of galactic collisions. Next, we'll delve into the mystery of the phantom star, a celestial object that seems to defy the laws of physics with its vanishing and reappearing act. Now, as we venture deeper into the mysteries of the MICE galaxies, we encounter a celestial enigma that seems to defy logic. The phantom star. This peculiar object has baffled astronomers with its ability to vanish and reappear in observations, leaving scientists scrambling to uncover the truth behind its elusive behavior. The phantom star's most striking feature is its unpredictable nature. At times, it shines brightly, easily visible among the countless stars in the galaxies. Then, without warning, it fades into obscurity as if it never existed. This vanishing act has led to intense scrutiny, with researchers proposing several theories to explain its strange behavior. One leading explanation is gravitational lensing, a phenomenon where the light from a distant star is bent and magnified by the gravitational field of a massive object, such as a black hole or another galaxy lying between the star and Earth. In this case, the phantom star's light could be temporarily amplified, making it appear brighter before fading as the alignment shifts. This cosmic trick of the light could create the illusion of a star that comes and goes. Another possibility is that the phantom star is a variable star, a type of star that undergoes significant changes in brightness over time. Some variable stars experience extreme fluctuations due to internal processes, such as pulsations or eruptions, which cause their luminosity to vary dramatically. If the phantom star falls into this category, its erratic brightness could be a natural part of its life cycle, though its extreme behavior would still make it a rare and fascinating object. The phantom star's mysterious nature also raises questions about the broader population of stars in the MICE galaxies. Could there be more stars like it, hidden in plain sight, their true nature obscured by their unpredictable behavior? Studying this star not only helps us understand its own peculiarities, but also sheds light on the complex dynamics at play in colliding galaxies, where gravitational interactions and stellar evolution create a rich tapestry of cosmic phenomena. As we ponder the secrets of the phantom star, we are reminded of the countless mysteries that still await discovery in the universe. Next, we'll explore the cosmic ring, a perfectly symmetrical structure that adds another layer of wonder to the MICE galaxies. Now, shifting our gaze to another marvel within the MICE galaxies, we encounter the cosmic ring, a structure so perfectly symmetrical it seems almost too precise to be natural. This stunning ring-shaped formation, nestled within one of the galaxies, stands out as a testament to the intricate and often violent processes that shape our universe. The cosmic ring's flawless symmetry has sparked intense curiosity among astronomers. How could such a perfect shape emerge from the chaos of colliding galaxies? One leading theory suggests that the ring formed as a result of a head-on collision between the larger galaxy and a smaller, passing galaxy. When a smaller galaxy plunges through the center of a larger one, the gravitational forces can send ripples through the stars and gas, creating a shockwave that propagates outward. This shockwave compresses the surrounding material, triggering the formation of new stars in a circular pattern, which we observe as the cosmic ring. Another possibility is that the ring is the result of a shockwave generated by a massive explosion, such as a supernova or the collision of two massive objects. These events can send powerful waves through the galaxy, compressing gas and dust into a ring-like structure. Over time, this compressed material begins to form stars, resulting in the luminous ring we see today. What makes the cosmic ring particularly fascinating is its rarity. While rings and arcs are not uncommon in the universe, a structure with such perfect symmetry is exceptionally rare. Its formation requires a precise alignment of forces and conditions, making it a cosmic jewel that offers a glimpse into the delicate balance of galactic interactions. The cosmic ring also serves as a reminder of the beauty that can emerge from destruction. In the chaos of galactic collisions, where stars are torn apart and gas clouds are flung into space, structures like this ring remind us that even in the most violent events, there is an underlying order and elegance. As we marvel at the cosmic ring, we are left to wonder what other hidden treasures lie within the MICE galaxies. Next, we'll turn our attention to the radio jet, a powerful stream of energy that reveals the dynamic forces at work in these colliding galaxies. Now, as we delve deeper into the mysteries of the MICE galaxies, we encounter one of the most awe-inspiring phenomena in the cosmos, the radio jet. This colossal stream of energy, stretching across vast distances, is a direct result of the immense power lurking at the heart of one of these colliding galaxies. The radio jet originates from the supermassive black hole at the galaxy's core. As matter spirals into the black hole, it doesn't just vanish. Instead, some of it is funneled into powerful jets that shoot out from the black hole's poles at nearly the speed of light. These jets are composed of charged particles and magnetic fields, creating a beam of energy so intense it can be detected across the universe. What makes this jet particularly remarkable is its scale. Stretching for thousands of light years, it pierces through the surrounding gas and dust, carving out a path of destruction and creation. As the jet interacts with the material in its path, it heats it up, triggering bursts of star formation and illuminating the surrounding regions. This interplay between destruction and creation is a hallmark of the dynamic processes at work in the MICE galaxies. The radio jet also serves as a cosmic lighthouse, emitting powerful radio waves that astronomers can detect from Earth. These emissions provide valuable insights into the behavior of supermassive black holes and the forces that shape galaxies. By studying the jet, scientists can better understand how black holes influence their surroundings and how they contribute to the evolution of galaxies over billions of years. One of the most intriguing aspects of the radio jet is its ability to shape its environment. The immense energy it carries can push gas and dust away, clearing out regions of space and influencing the formation of new stars and planets. At the same time, the jet's interaction with the surrounding material can create shock waves that compress gas, triggering the birth of new stars in its wake. As we observe the radio jet, we are reminded of the incredible forces at play in the universe. It's a testament to the power of supermassive black holes and their ability to shape the cosmos on a grand scale. Next, we'll explore the dusty veil, a thick shroud of dust that obscures part of the galaxies, revealing yet another layer of complexity in this cosmic collision. Now shifting our gaze to another enigmatic feature of the MICE galaxies, we encounter the dusty veil, a thick shroud of dust that cloaks portions of these colliding galaxies. This veil is not just a simple obstruction. It's a dynamic and complex structure that plays a crucial role in shaping our understanding of galactic interactions. The dusty veil is composed of countless tiny particles of dust and gas, which scatter and absorb light from the stars and other objects behind it. This makes it incredibly challenging for astronomers to observe what lies beyond, effectively hiding entire regions of the galaxies from view. However, this obscuring effect is not just a hindrance, it's also a treasure trove of information. By studying how the dust interacts with light, scientists can infer the composition, density, and temperature of the material within the veil. One of the most fascinating aspects of the dusty veil is its origin. This thick layer of dust likely formed as a result of the ongoing collision between the two galaxies. As the galaxies merge, their gas and dust clouds collide and compress, creating dense regions where new stars can form. At the same time, the collision generates shockwaves that stir up the dust, spreading it across vast areas and creating the veil we observe today. The presence of the dusty veil also reveals how the collision has disrupted the structure of the galaxies. In regions where the veil is thickest, the gravitational forces from the collision have likely caused gas and dust to accumulate, forming dense pockets that could eventually give rise to new stars or even entire star clusters. This process highlights the dual nature of galactic collisions, destructive on one hand, but also a catalyst for new creation. Interestingly, the dusty veil doesn't just obscure light, it also emits it. When dust particles are heated by nearby stars or shockwaves, they radiate infrared light which can penetrate the veil and be detected by telescopes. This infrared emission provides a unique window into the hidden regions of the galaxies, allowing astronomers to map the distribution of dust and study its properties in detail. As we peel back the layers of the dusty veil, we gain a deeper appreciation for the complexity of the MICE galaxies. This seemingly simple curtain of dust is in fact a dynamic and evolving structure that holds clues to the forces shaping these colliding galaxies. Next, we'll turn our attention to the warped disk, a striking feature that showcases the dramatic effects of gravitational forces on the galaxy's structure. Now turning to another remarkable feature of the MICE galaxies, we encounter the warped disk, a striking and highly distorted structure of stars and gas that defies the typical flat, spiral shape we associate with galaxies. This warped disk is a vivid testament to the immense gravitational forces at play during the collision of these two galaxies, offering a glimpse into the chaotic yet fascinating processes that shape galactic evolution. The warped disk is a result of the intense gravitational tug-of-war between the two galaxies as they merge. As they spiral closer together, their gravitational fields interact in complex ways, pulling and twisting the stars and gas within them. This gravitational dance has stretched and bent the disk of one of the galaxies into an unusual, almost contorted shape. Unlike the orderly, flat disks seen in isolated galaxies, this warped structure resembles a twisted ribbon, with its edges curving upward and downward in dramatic arcs. What makes the warped disk particularly intriguing is its role in revealing the dynamics of galactic collisions. The distortion isn't just a visual oddity, it's a direct consequence of the transfer of energy and momentum between the two galaxies. As they collide, the gravitational forces redistribute the stars and gas, creating regions of intense compression and expansion. This process not only warps the disk but also triggers the formation of new stars and star clusters, adding another layer of complexity to the galaxy's evolution. The unusual shape of the warped disk also provides valuable insights into the distribution of dark matter within the galaxies. Dark matter, which doesn't emit light but exerts gravitational influence, plays a key role in shaping the structure of galaxies. By studying the warping of the disk, astronomers can infer the distribution and density of dark matter, helping them better understand its impact on galactic dynamics. Moreover, the warped disk serves as a reminder of the transformative power of galactic collisions. While these events are often destructive, they also drive the creation of new structures and phenomena. The warped disk is a living example of how gravity can sculpt the universe, turning chaos into beauty and complexity. As we marvel at the warped disk, we're reminded that the MICE galaxies are more than just a pair of colliding galaxies. They're a cosmic laboratory, offering a front-row seat to the forces that shape the universe. Next, we'll explore the supernova graveyard, a region filled with the remnants of ancient stellar explosions that tell yet another chapter in the story of these extraordinary galaxies. Now shifting our gaze to another fascinating feature of the MICE galaxies, we arrive at the supernova graveyard, a hauntingly beautiful region scattered with the remnants of ancient stellar explosions. This area is a testament to the violent yet creative forces unleashed during the collision of these two galaxies, offering a glimpse into the life and death of stars on a cosmic scale. The supernova graveyard is a sprawling expanse filled with the glowing remnants of supernova explosions so powerful they outshine entire galaxies for brief moments. These remnants, often appearing as delicate filaments and glowing clouds of gas, are the final echoes of massive stars that ended their lives in spectacular fashion. The collision of the MICE galaxies played a pivotal role in triggering this wave of supernova. As the galaxies merged, the intense gravitational forces compressed vast clouds of gas, igniting a burst of star formation. Many of these newly formed stars were massive, burning through their fuel quickly and ending their lives in dramatic supernova explosions. What makes this region particularly captivating is the sheer scale of destruction and creation it represents. Each supernova remnant tells a story of a star's explosive demise, scattering heavy elements like iron, gold, and uranium into the surrounding space. These elements, forged in the hearts of stars and dispersed by their deaths, become the building blocks for new stars, planets, and even life itself. In this way, the supernova graveyard is not just a site of destruction, but also a cradle of future cosmic possibilities. The glowing remnants also provide astronomers with a unique opportunity to study the aftermath of supernova. By analyzing the light emitted by these remnants, scientists can determine the composition of the ejected material, the energy released during the explosion, and the impact of these events on the surrounding environment. This information helps us understand the life cycles of stars and the role supernova play in shaping galaxies. Moreover, the supernova graveyard serves as a vivid reminder of the interconnectedness of cosmic events. The collision of the MICE galaxies set off a chain reaction triggering star formation, leading to supernova and ultimately enriching the galaxies with the elements necessary for future generations of stars and planets. It's a cycle of creation and destruction that underscores the dynamic nature of the universe. As we reflect on the supernova graveyard, we're reminded that even in the aftermath of destruction, there is beauty and potential. These glowing remnants are not just relics of the past, but also seeds for the future. Next, we'll explore the cosmic web, a vast and intricate structure of gas and dust that spans the galaxies, revealing yet another layer of complexity in this cosmic collision. Now turning our attention to the cosmic web, we encounter one of the most intricate and awe-inspiring structures within the MICE galaxies. This vast, web-like network of gas and dust stretches across the galaxies, weaving a tapestry that reveals the hidden architecture of the universe. The cosmic web is not just a random arrangement of material, it's a direct result of the colossal collision between the two galaxies, offering a unique window into how matter is distributed on a cosmic scale. The formation of the cosmic web can be traced back to the immense gravitational forces unleashed during the galaxy's collision. As the two galaxies spiraled toward each other, their gravitational pull stretched and twisted the surrounding gas and dust, creating a complex network of filaments. These filaments, resembling the strands of a spider's web, connect dense regions of star formation and supernova remnants, forming a bridge between the galaxies. This structure is a vivid illustration of how gravity shapes the universe, pulling matter into vast, interconnected networks. What makes the cosmic web particularly fascinating is its role in the distribution of matter. The filaments act as cosmic highways, channeling gas and dust from one region to another. This flow of material fuels star formation in some areas while leaving others sparse and empty. By studying the cosmic web, astronomers can map the movement of matter across the galaxies, gaining insights into how galaxies grow and evolve over time. It's a dynamic system, constantly reshaped by the forces of gravity and the energy released during the collision. The cosmic web also provides clues about the larger structure of the universe. On a grand scale, the universe itself is thought to be filled with similar web-like structures, connecting galaxies and galaxy clusters across vast distances. The MICE Galaxies cosmic web serves as a miniature version of this cosmic architecture, allowing scientists to study these phenomena up close. By understanding how the web forms and evolves, we can piece together the story of how the universe organizes itself, from the smallest filaments to the largest superclusters. As we marvel at the cosmic web, we're reminded of the delicate balance between chaos and order in the universe. What may appear as a random tangle of gas and dust is in fact a carefully orchestrated dance of matter, shaped by the forces of nature. This web not only connects the galaxies but also connects us to the broader mysteries of the cosmos. Next, we'll uncover the secrets of the Phantom Galaxy, a faint and ghostly presence hidden within the MICE galaxies, revealing yet another layer of this cosmic collision's complexity. Now shifting our gaze to the Phantom Galaxy, we uncover a faint and ghostly presence lurking within the chaos of the MICE galaxies. This elusive galaxy, barely visible against the backdrop of its brighter neighbors, offers a haunting glimpse into the process of galactic cannibalism, a phenomenon where larger galaxies consume smaller ones. The Phantom Galaxy is believed to have been absorbed during the collision of the MICE galaxies, its stars and gas now scattered and interwoven with the larger structures around it. The discovery of the Phantom Galaxy raises intriguing questions about how galaxies grow and evolve. As the MICE galaxies collided, their immense gravitational forces likely pulled in this smaller galaxy, tearing it apart and redistributing its material. This process, known as galactic cannibalism, is a common occurrence in the universe where larger galaxies often absorb smaller ones to fuel their growth. The Phantom Galaxy's remnants serve as a cosmic fossil, preserving evidence of this violent merger and offering clues about the history of the MICE galaxies. What makes the Phantom Galaxy particularly fascinating is its faint, ghostly appearance. Unlike the bright, star-filled regions of the MICE galaxies, this galaxy's remnants are diffuse and difficult to detect. Its stars are spread thin, blending into the surrounding material, while its gas has been stretched into long, wispy filaments. This ghostly structure highlights the destructive yet creative nature of galactic collisions, where old structures are torn apart to form new ones. The presence of the Phantom Galaxy also sheds light on the hierarchical nature of galaxy formation. Over billions of years, galaxies grow by merging with others, building up their mass and complexity. The Phantom Galaxy's absorption into the MICE galaxies is a snapshot of this ongoing process, showing how smaller galaxies contribute to the evolution of larger ones. By studying its remnants, astronomers can piece together the timeline of the collision and better understand how galaxies like the MICE galaxies came to be. As we reflect on the Phantom Galaxy, we're reminded of the dynamic and ever-changing nature of the universe. What once was a distinct galaxy is now a faint echo, its story written in the stars and gas of the MICE galaxies. This ghostly presence not only deepens our understanding of galactic cannibalism, but also connects us to the broader narrative of cosmic evolution. Next, we'll explore the magnetic anomaly, a region of intense magnetic fields that adds another layer of mystery to the MICE galaxy's collision. Now turning to the magnetic anomaly, we encounter one of the most puzzling features within the MICE galaxies, a region where the magnetic field is unusually intense, defying expectations and challenging our understanding of galactic dynamics. This magnetic hotspot, detected through advanced observations, stands out as a cosmic enigma, its origins and effects still shrouded in mystery. The formation of this magnetic anomaly is thought to be tied to the violent collision of the MICE galaxies. As the two galaxies spiraled into each other, their magnetic fields became tangled and amplified, creating pockets of extreme magnetic activity. Some scientists suggest that shock waves from the collision compressed and energized these fields, while others propose that the anomaly could be linked to the supermassive black holes at the galaxy's cores, whose powerful jets might have contributed to the magnetic intensification. What makes this anomaly particularly intriguing is its potential to influence the surrounding environment. Strong magnetic fields can shape the flow of gas and dust, guiding the movement of material and even affecting the birth of new stars. In this region, the magnetic field is so powerful that it may be redirecting the flow of gas, creating dense pockets where star formation could be triggered. This raises the possibility that the anomaly is not just a passive feature but an active player in the ongoing evolution of the MICE galaxies. The impact of the magnetic anomaly extends beyond star formation. Its intense fields could also affect the behavior of cosmic rays and charged particles, altering how energy is distributed throughout the galaxies. This, in turn, might influence the growth of structures like the luminous bridge connecting the two galaxies or the ghostly filaments of the phantom galaxy. By studying this anomaly, astronomers hope to uncover how magnetic fields shape the life cycle of galaxies and their components. As we explore the magnetic anomaly, we're reminded of the intricate interplay of forces at work in the universe. From the tiniest particles to the largest structures, magnetism plays a crucial role in shaping the cosmos. This anomaly, with its extraordinary strength and mysterious origins, offers a unique window into the hidden forces driving galactic evolution. Next, we'll delve into the cosmic lighthouse, a pulsar whose rhythmic pulses illuminate the mysteries of the MICE galaxies. Now shifting our gaze to the cosmic lighthouse, we encounter a celestial marvel that pulses with the precision of a cosmic metronome. This pulsar, a rapidly spinning neutron star, emits regular bursts of energy that cut through the darkness of space like a beacon. Discovered through meticulous observations of the MICE galaxies, this pulsar stands as a testament to the extraordinary phenomena born from the chaos of galactic collisions. The formation of this pulsar traces back to the explosive death of a massive star. When such a star exhausts its fuel, it collapses under its own gravity, triggering a supernova. What remains is a neutron star, a dense, city-sized object spinning at incredible speeds. In the case of the cosmic lighthouse, this neutron star's magnetic field channels energy into focused beams, which sweep across space like the beam of a lighthouse. Each time these beams point toward Earth, we detect a pulse of radiation, creating the rhythmic flashes that define a pulsar. What makes this pulsar particularly fascinating is its role as a cosmic beacon. Its regular pulses serve as a natural clock, allowing astronomers to measure time with extraordinary precision. This precision has made pulsars invaluable tools for studying the universe. For instance, they've been used to test Einstein's theory of general relativity and to map the distribution of matter in the cosmos. The cosmic lighthouse, with its steady rhythm, offers a unique window into the fundamental workings of space and time. Beyond its scientific utility, the pulsar's energy emissions also illuminate its surroundings. The intense beams of radiation interact with nearby gas and dust, creating glowing halos and shockwaves that ripple through the MICE galaxies. These interactions provide clues about the environment around the pulsar, revealing how such objects influence their cosmic neighborhoods. As we marvel at the cosmic lighthouse, we're reminded of the intricate balance between destruction and creation in the universe. From the ashes of a dying star emerges a beacon that guides our understanding of the cosmos. Its rhythmic pulses not only mark the passage of time, but also connect us to the vast, dynamic tapestry of the universe. Next, we'll explore the starless void, a mysterious region where the usual rules of galactic structure seem to break down. Now turning to the starless void, we encounter one of the most enigmatic features of the MICE galaxies, a vast, seemingly empty region that defies our expectations of what a galaxy should look like. Unlike the bustling star clusters and glowing nebulae we've explored so far, this void is a stark contrast, a cosmic desert where stars are conspicuously absent. But how does such a region form in the midst of two colliding galaxies teeming with activity? One leading theory suggests that the starless void may have been carved out by a cataclysmic supernova explosion. When a massive star reaches the end of its life, It can explode with such force that it blows away surrounding gas and dust, leaving behind a cleared-out region. Over time, this area might struggle to accumulate enough material to form new stars, resulting in the eerie emptiness we observe today. Another possibility is that the void is the result of intense gravitational forces at play during the collision of the MICE galaxies. As the two galaxies interact, their gravitational fields can create regions of extreme disruption, where stars and gas are flung outward or pulled into other areas. This gravitational tug-of-war could leave behind pockets of space that appear unnaturally barren, as if the very fabric of the galaxy has been stretched and distorted. What makes the starless void particularly intriguing is its potential to challenge our understanding of galactic evolution. Typically, galaxies are thought to be dynamic, star-forming environments, but this void suggests that under certain conditions, they can also harbor regions of profound stillness. Studying such areas could provide insights into how galaxies evolve over time, especially during violent events like collisions. As we peer into this mysterious expanse, we're reminded that even in the chaos of the universe, there are moments of quiet and emptiness. The starless void stands as a testament to the complex interplay of forces that shape galaxies, offering a glimpse into the delicate balance between creation and destruction. Next, we'll delve into the galactic tail, a stunning structure born from the tidal forces of the collision, stretching across the cosmos like a celestial ribbon. Now shifting our gaze to the galactic tail, we uncover one of the most visually striking features of the MICE galaxies, a long, sweeping arc of stars and gas that stretches far beyond the main bodies of the colliding galaxies. This celestial ribbon, glowing faintly against the backdrop of space, is a direct result of the immense tidal forces unleashed during the collision. But what exactly are tidal forces, and how do they sculpt such a breathtaking structure? Tidal forces arise when the gravitational pull of one massive object, like a galaxy, tugs unevenly on another. In the case of the MICE galaxies, as the two galaxies spiral closer together, their gravitational fields interact in a cosmic dance, stretching and pulling material from each other. This process creates long streams of stars and gas, which are flung outward into space, forming the galactic tail we see today. What makes this tail so fascinating is not just its beauty, but also the story it tells about the collision itself. The length and shape of the tail provide clues about the speed and angle at which the galaxies collided. For instance, a longer tail might suggest a more glancing blow, while a shorter, denser tail could indicate a more direct impact. By studying these features, astronomers can piece together the history of the collision, much like detectives reconstructing a cosmic crime scene. The galactic tail also serves as a cosmic conveyor belt, transporting material from one galaxy to the other. As stars and gas are pulled into the tail, they may eventually fall back into one of the galaxies, fueling new star formation or even feeding the supermassive black holes at their centers. This exchange of material is a key part of galactic evolution, showing how collisions can reshape galaxies over billions of years. As we marvel at this stunning structure, we're reminded of the incredible forces at work in the universe. The galactic tail is not just a remnant of destruction, but also a symbol of creation, a testament to the dynamic and ever-changing nature of galaxies. Next, we'll explore the cosmic eye, a ring-shaped structure that resembles a celestial iris, offering yet another glimpse into the mysteries of galactic collisions. Now turning our attention to the cosmic eye, we encounter one of the most mesmerizing structures within the MICE galaxies, a perfect ring-shaped formation that resembles a celestial iris gazing out into the cosmos. This stunning feature, with its symmetrical and almost artistic appearance, stands as a testament to the incredible forces at play during galactic collisions. But how does such a perfect ring form in the chaos of colliding galaxies? The cosmic eye is believed to have originated from one of two possible scenarios. The first theory suggests that it formed when a smaller galaxy collided head-on with one of the MICE galaxies. This direct impact would have sent shockwaves rippling through the larger galaxy, compressing gas and dust into a dense ring. Over time, this ring began to glow as new stars ignited within it, creating the luminous structure we observe today. The second theory proposes that the ring is the result of a shockwave generated by the collision of the two main galaxies. As the galaxies spiraled closer together, the immense gravitational forces could have triggered a wave of star formation in a circular pattern, much like a stone creating ripples in a pond. This process would have left behind a glowing ring of young stars, giving the cosmic eye its striking appearance. What makes the cosmic eye particularly fascinating is its rarity. Perfect ring structures like this are uncommon in the universe, making it a valuable subject for astronomers studying galactic collisions. Its symmetry and brightness provide clues about the conditions that led to its formation, offering insights into the dynamics of such cosmic events. Beyond its scientific significance, the cosmic eye captivates with its sheer beauty. Its glowing ring, set against the dark expanse of space, serves as a reminder of the artistry hidden within the chaos of the universe. As we study this celestial marvel, we gain a deeper appreciation for the intricate processes that shape galaxies over billions of years. With the cosmic eye now in focus, we prepare to explore another enigmatic feature of the MICE galaxies, the phantom jet, a faint stream of particles that appears and disappears, challenging our understanding of galactic activity. Now shifting our gaze to the phantom jet, we encounter one of the most puzzling phenomena in the MICE galaxies, a faint stream of particles that seems to flicker in and out of existence. This elusive jet, appearing and disappearing without warning, has left astronomers both intrigued and baffled. What could cause such a transient and ghostly feature in the midst of these colliding galaxies? One leading explanation points to the possibility of intermittent activity from a supermassive black hole. At the heart of one of the MICE galaxies, a black hole might be sporadically ejecting jets of particles into space. These jets, powered by the black hole's immense gravitational pull, could flare up and then fade as the black hole's feeding cycle fluctuates. This on and off behavior would explain why the phantom jet appears to vanish and reappear over time. Another intriguing theory involves gravitational lensing, a phenomenon where the immense gravity of a massive object like a galaxy or black hole bends and magnifies light from objects behind it. In this case, the light from a distant jet could be passing through a region of intense gravitational distortion, causing it to appear and disappear as the alignment shifts. This cosmic trick of light might be creating the illusion of a phantom jet, adding another layer of mystery to the MICE galaxies. The phantom jet's transient nature makes it a challenging subject to study, but it also offers a unique opportunity to explore the dynamic processes at work in galactic collisions. By observing its behavior, astronomers hope to uncover more about the mechanisms driving black hole activity and the role of gravitational lensing in shaping what we see in the universe. As we ponder the mysteries of the phantom jet, we're reminded of how much remains unknown about the cosmos. Its fleeting presence serves as a humbling reminder that even in the vastness of space, there are still phenomena that defy easy explanation. With this enigmatic feature now in focus, we prepare to delve into another fascinating object, the Starburst Nebula, a glowing region of intense star formation that reveals the fiery aftermath of galactic collisions. Now turning to the Starburst Nebula, we find ourselves gazing at one of the most spectacular sights in the MICE galaxies, a glowing cloud of gas and dust where stars are being born at an astonishing rate. This nebula, illuminated by the fiery light of countless newborn stars, is a vivid reminder of the transformative power of galactic collisions. But what exactly makes this region such a hotbed of stellar activity? And what can it teach us about the birth of stars? The collision between the two galaxies that make up the MICE galaxies has created the perfect conditions for a starburst nebula to form. As the galaxies interact, their gravitational forces compress vast clouds of gas and dust, triggering a chain reaction of star formation. These dense clouds, once stable and quiet, are now collapsing under the immense pressure, igniting the birth of new stars. The result is a dazzling display of light and energy as young stars burst into existence, heating the surrounding gas and causing it to glow brightly. This intense star formation reveals a great deal about the conditions needed for stars to form. For a nebula to become a starburst region, it requires an abundance of raw materials, primarily hydrogen gas, and a catalyst to set the process in motion. In the case of the MICE galaxies, the collision provided that catalyst, compressing the gas and dust to the point where gravity could take over, pulling the material together to form stars. The sheer scale of this activity is staggering, with thousands of stars being born in a relatively short period of time, compared to the more gradual pace of star formation in undisturbed galaxies. The Starburst Nebula also offers a glimpse into the life cycle of stars. Within its glowing clouds, we can observe stars at every stage of development, from dense protostars still shrouded in gas and dust to fully formed stars blazing with energy. This diversity provides astronomers with a unique opportunity to study the processes that govern star birth and evolution, shedding light on how stars like our own Sun came to be. As we marvel at the beauty and complexity of the Starburst Nebula, we're reminded of the dynamic and ever-changing nature of the universe. This glowing region is not just a testament to the power of galactic collisions, but also a window into the fundamental processes that shape the cosmos. With this fiery spectacle now in focus, we prepare to explore another intriguing feature, the cosmic spiral, a mysterious structure that hints at the intricate dance of gravity and matter in the MICE galaxies. Now shifting our gaze to the cosmic spiral, we encounter a mesmerizing structure that seems to defy the chaos of the colliding galaxies. This spiral-shaped formation, with its intricate and delicate patterns, stands out as a striking contrast to the turbulent surroundings of the MICE galaxies. But what exactly is this spiral, and how did it come to be? Is it a remnant of a smaller galaxy swallowed up in the collision? Or is it a unique feature sculpted by the forces at play during this cosmic encounter? The cosmic spiral's elegant shape immediately draws comparisons to the familiar spiral arms of galaxies like our own Milky Way. However, its presence within the MICE galaxies raises intriguing questions. One possibility is that this spiral is the lingering trace of a smaller galaxy that was torn apart and absorbed during the collision. As the two larger galaxies interacted, their gravitational forces could have stretched and twisted the smaller galaxy's structure, leaving behind this spiral as a ghostly echo of its former self. This scenario would explain the spiral's distinct appearance, as well as its alignment with the larger galactic structures. Alternatively, the cosmic spiral might be a completely new feature, born directly from the collision itself. The immense gravitational forces and tidal interactions between the two galaxies could have compressed and twisted gas and dust into this spiral shape. This process, known as tidal distortion, often creates stunning and unexpected formations during galactic mergers. If this is the case, the cosmic spiral serves as a testament to the creative power of cosmic collisions, where destruction gives rise to beauty. The intricate patterns within the spiral offer further clues about its origins. Detailed observations reveal swirling arms of gas and dust, dotted with pockets of star formation. These regions, glowing with the light of young stars, suggest that the spiral is not just a static structure but an active site of stellar birth. The interplay of gravity, pressure, and radiation within the spiral's arms creates the perfect conditions for new stars to ignite, adding another layer of complexity to this already fascinating object. As we study the cosmic spiral, we're reminded of the delicate balance between chaos and order in the universe. This structure, whether a remnant of a lost galaxy or a product of the collision, showcases the intricate dance of matter and energy that shapes the cosmos. Its beauty and mystery invite us to ponder the countless stories hidden within the MICE galaxies, each one a piece of the larger puzzle of galactic evolution. With a cosmic spiral now in focus, we prepare to explore another enigmatic feature, the dark cloud, a massive and shadowy presence that holds secrets of its own. Now turning our attention to the dark cloud, we encounter a massive and shadowy presence that looms within the MICE galaxies. This colossal cloud of gas and dust, dense and opaque, stands in stark contrast to the glowing structures around it. But what exactly is this dark cloud, and what secrets does it hold about the ongoing collision of these galaxies? The dark cloud likely formed from the vast reservoirs of gas and dust present in the MICE galaxies before their collision. As the two galaxies interacted, their gravitational forces could have compressed these materials into dense pockets, creating regions where light struggles to penetrate. Over time, these pockets may have grown into the massive cloud we observe today, a testament to the chaotic yet creative forces at play during galactic mergers. One of the most intriguing possibilities is that the dark cloud could be on the verge of collapsing under its own gravity. When such a cloud reaches a critical density, it can trigger the birth of new stars. The immense pressure within the cloud causes gas and dust to clump together, eventually igniting nuclear fusion and giving rise to young, bright stars. If this process is underway within the dark cloud, it could become a stellar nursery, adding a burst of new light to the already dynamic MICE galaxies. However, the dark cloud's dense structure also poses challenges for astronomers. Its thick layers of dust obscure the light from objects behind it, making it difficult to study the regions beyond. This obscuration can hide important details about the galaxy's structure and evolution, leaving scientists to rely on indirect methods such as infrared observations to peer through the darkness. Despite these challenges, the dark cloud offers valuable insights into the conditions necessary for star formation and the role of dust in shaping galactic landscapes. As we examine the dark cloud, we're reminded of the dual nature of such structures, both obstacles and opportunities. While it blocks our view, it also holds the potential for new stellar life, a reminder that even in the darkest corners of the universe, creation is always possible. With this enigmatic cloud now in focus, we prepare to explore another fascinating feature, the phantom cluster, a mysterious group of stars that seems to vanish and reappear, challenging our understanding of the cosmos. Now shifting our gaze to the phantom cluster, we encounter one of the most baffling phenomena in the MICE galaxies, a group of stars that seems to flicker in and out of existence. This mysterious cluster, appearing and disappearing in observations, challenges our understanding of how stars behave and interact in the cosmos. What could cause such an elusive display, and what does it reveal about the forces at work in these colliding galaxies? One possible explanation for the phantom cluster's behavior lies in the phenomenon of gravitational lensing. When a massive object like a black hole or a dense cluster of stars lies between us and the phantom cluster, its immense gravity can bend and magnify the light from the stars behind it. This effect can create illusions, making stars appear brighter, dimmer, or even vanish entirely depending on the alignment of the objects. If the lensing object moves or changes, the stars in the phantom cluster might seem to flicker or disappear, creating the ghostly effect we observe. Another intriguing possibility is that the phantom cluster is home to variable stars whose brightness fluctuates over time. Some stars, like Cepheid variables or eclipsing binaries, naturally brighten and dim in predictable patterns. If the phantom cluster contains a high concentration of such stars, their combined light could create the illusion of the entire cluster vanishing and reappearing. This explanation would make the phantom cluster not just a cosmic mystery, but also a fascinating laboratory for studying stellar behavior. The phantom cluster's elusive nature also raises questions about the role of dust and gas in obscuring our view. The MICE galaxies are rich in interstellar material, and dense clouds of dust could periodically block our line of sight to the cluster, making it seem as though the stars have disappeared. When the clouds shift or thin out, the cluster would reappear, adding another layer of complexity to this cosmic enigma. As we ponder the phantom cluster, we're reminded of the universe's ability to surprise and challenge us. Whether through the bending of light, the flickering of stars, or the shifting of cosmic dust, this mysterious cluster invites us to look deeper and question what we think we know. With this celestial puzzle now in focus, we prepare to explore another extraordinary feature, the cosmic arc, a glowing structure that stretches across the galaxies, offering new insights into the forces shaping the universe. Now turning to the cosmic arc, we find ourselves captivated by one of the most visually stunning structures in the MICE galaxies. This glowing arc of gas and stars stretches gracefully across the vast expanse, a luminous ribbon that seems to defy the chaos of the colliding galaxies around it. Its ethereal beauty is matched only by its rarity, making it a true cosmic treasure. The formation of the cosmic arc is a story written in the language of gravity and motion. One leading theory suggests that it was born from the immense tidal forces generated by the collision of the two galaxies. As these galaxies pulled and twisted each other, vast streams of gas and stars were flung outward, creating this breathtaking arc. Another possibility is that a shock wave, rippling through the galaxies from a massive explosion or collision, compressed and heated the surrounding material, causing it to glow and form this radiant structure. What makes the cosmic arc so remarkable is not just its origin, but its sheer elegance. Unlike the chaotic swirls and knots often seen in colliding galaxies, the arc's smooth, curved shape stands out as a testament to the delicate balance of forces at play. Its glow, a mix of ionized gas and young, hot stars, paints a vivid picture of the dynamic processes shaping the universe. Rarity adds to its allure. Structures like the cosmic arc are not commonly observed, making it a unique window into the physics of galactic interactions. By studying its composition, brightness, and structure, astronomers can gain insights into how galaxies evolve and how new stars are born in the wake of cosmic collisions. As we marvel at the cosmic arc, we're reminded of the universe's ability to create beauty even in the midst of chaos. This glowing ribbon of light invites us to appreciate the artistry of the cosmos and to continue exploring the mysteries it holds. With this celestial wonder now in focus, we prepare to uncover the secrets of the radio ring, a structure that emits powerful waves of energy, revealing yet another layer of the MICE galaxy's complexity. Now shifting our gaze to the radio ring, we encounter a structure that hums with the energy of the unseen. This ring-shaped phenomenon, glowing faintly in the radio spectrum, is a testament to the invisible forces at work in the MICE galaxies. Unlike the cosmic arc, which dazzles with visible light, the radio ring reveals its secrets through the whispers of radio waves, offering a glimpse into the hidden layers of galactic activity. At the heart of this mysterious ring lies a supermassive black hole, a cosmic powerhouse that shapes its surroundings in profound ways. The radio ring is thought to be a byproduct of the black hole's immense gravitational pull and its voracious appetite for matter. As material spirals toward the black hole, it heats up and emits intense radiation, some of which escapes in the form of radio waves. These waves, traveling across vast distances, form the glowing ring we observe today. But how exactly does this ring take shape? One theory suggests that the black hole's powerful jets, streams of particles ejected at nearly the speed of light, collide with surrounding gas and dust. This collision creates shockwaves that ripple outward, compressing and heating the material. Over time, these shockwaves carve out a ring-like structure, which then emits the radio waves we detect. Another possibility is that the ring is a remnant of an ancient explosion, a cosmic echo of a past event that left its mark on the galaxies. What makes the radio ring particularly fascinating is its connection to the broader dynamics of the MICE galaxies. The ring's emissions provide a unique window into the behavior of supermassive black holes and their role in galactic evolution. By studying its size, shape, and intensity, astronomers can piece together the story of how black holes influence their surroundings, from triggering star formation to shaping the structure of entire galaxies. As we ponder the radio ring, we're reminded that the universe speaks in many languages, some visible, some hidden. This glowing ring of radio waves invites us to listen closely, to uncover the secrets of the cosmos that lie beyond the reach of our eyes. With this enigmatic structure now in focus, we prepare to delve into the ghostly stream, a faint trail of stars and gas that tells yet another chapter in the story of the MICE galaxies. Now turning to the ghostly stream, we encounter a delicate and almost ethereal trail of stars and gas winding its way through the MICE galaxies. This faint ribbon of light, barely visible against the backdrop of space, tells a story of cosmic cannibalism and the relentless forces that shape galaxies over billions of years. The ghostly stream is believed to be the remnants of a smaller galaxy that was torn apart and absorbed by one of the larger galaxies in this colliding pair. As the smaller galaxy was pulled in by gravity, its stars and gas were stretched into a long, thin stream, leaving behind this ghostly signature of its demise. The formation of the ghostly stream offers a fascinating glimpse into the process of galactic mergers. When two galaxies collide, the gravitational forces at play can be both destructive and creative. In this case, the smaller galaxy was unable to withstand the immense pull of its larger neighbor, and its material was scattered across space, forming this faint but enduring trail. Over time, the stars and gas in the stream may be absorbed into the larger galaxy, contributing to its growth and evolution. This process, known as galactic cannibalism, is a key mechanism by which galaxies grow and change over cosmic time. What makes the ghostly stream particularly significant is its role in helping astronomers understand the dynamics of galactic mergers. By studying its structure and composition, scientists can piece together the history of the collision and learn more about how galaxies interact and evolve. The stream's faint glow also provides clues about the distribution of dark matter, the invisible substance that makes up much of the universe's mass. As the smaller galaxy was torn apart, its dark matter would have influenced the shape and movement of the stream, leaving behind subtle traces that can be detected through careful observation. The ghostly stream serves as a reminder that even the faintest structures in the universe can hold profound secrets. Its delicate appearance belies the violent forces that created it, offering a window into the complex and often chaotic processes that shape the cosmos. As we continue our journey through the MICE galaxies, the ghostly stream invites us to reflect on the intricate dance of gravity, time, and matter that defines the universe we inhabit. With this haunting trail now in view, we prepare to explore the cosmic knot, a dense and mysterious region that holds yet another piece of the galactic puzzle. Now shifting our gaze to the cosmic knot, we encounter a tightly packed region of gas and stars, a dense and intricate structure that stands out amidst the chaos of the colliding MICE galaxies. This compact knot, glowing with the energy of countless stars, is a fascinating example of how galactic collisions can create pockets of intense activity. The cosmic knot is not just a random clump of material, it's a potential cradle for new star formation, a place where the raw ingredients of the universe come together under the influence of gravity and pressure. The formation of the cosmic knot likely began with the collision of the two galaxies. As the galaxies interacted, their gas clouds were compressed, creating regions of higher density. In some areas, this compression led to the formation of dense knots like this one. Over time, the gravitational pull within these knots can cause the gas and dust to collapse further, igniting the birth of new stars. This process is a key part of how galaxies evolve, as these knots can eventually grow into star clusters or even larger structures within the galaxy. What makes the cosmic knot particularly intriguing is its potential to become a new star cluster. The conditions within the knot, high density, intense pressure, and abundant gas, are ideal for star formation. As gravity continues to pull the material together, the knot could give rise to hundreds or even thousands of new stars, creating a bright and dynamic cluster that would stand out against the backdrop of the galaxies. This process is a reminder of how even the most chaotic events in the universe can lead to the creation of something beautiful and enduring. The compact structure of the cosmic knot also offers valuable insights into the mechanics of galactic collisions. By studying its shape and composition, astronomers can learn more about how gas and stars behave under extreme conditions. The knot's dense core and surrounding filaments provide clues about the forces at play during the collision, helping scientists piece together the story of how the MICE galaxies came to be. It's a testament to the power of gravity and the intricate dance of matter that shapes the cosmos. As we examine the cosmic knot, we're reminded of the incredible potential for creation that exists within the chaos of the universe. This dense, glowing region is not just a remnant of a collision. It's a beacon of possibility, a place where new stars and new worlds may one day emerge. With the cosmic knot now in focus, we turn our attention to the Phantom Nebula, a mysterious and elusive structure that challenges our understanding of galactic interactions. Now turning to the Phantom Nebula, we encounter one of the most enigmatic structures in the MICE galaxies. This nebula, unlike any other, has a peculiar habit of vanishing and reappearing in observations, leaving astronomers both puzzled and fascinated. Its ghostly presence challenges our understanding of how nebulae behave, raising questions about the forces at play in this colliding galactic system. The Phantom Nebula's disappearing act could be explained by a phenomenon known as variable illumination. In this scenario, the nebula's glow is influenced by the light from nearby stars or other celestial objects. When these light sources dim or are obscured, the nebula appears to vanish. Conversely, when the light intensifies or becomes unobstructed, the nebula reemerges, creating the illusion of a phantom structure. This interplay of light and shadow adds a layer of mystery to the nebula's behavior, making it a captivating subject for further study. Another possible explanation lies in the realm of gravitational lensing. The intense gravitational forces generated by the colliding galaxies could bend and distort light in such a way that the nebula becomes temporarily invisible from our vantage point. As the alignment of objects shifts over time, the lensing effect might weaken, allowing the nebula to reappear. This cosmic sleight of hand demonstrates how gravity can manipulate our perception of the universe, turning even the most familiar objects into fleeting apparitions. The Phantom Nebula's elusive nature also raises intriguing questions about its composition and structure. Is it a dense cloud of gas and dust, or a more diffuse region that only becomes visible under specific conditions? Could it be a remnant of the collision, or a transient feature formed by the turbulent forces at work in the MICE galaxies? Each observation brings us closer to unraveling its secrets, but the nebula continues to defy easy explanation. As we ponder the mysteries of the Phantom Nebula, we're reminded of how much remains unknown about the universe. Its vanishing act serves as a humbling reminder that even with advanced technology, the cosmos still holds countless surprises. With the Phantom Nebula now in focus, we prepare to explore the warped jet, a structure that bends the rules of physics and challenges our understanding of galactic dynamics. Now shifting our gaze to the warped jet, we encounter a phenomenon that seems to defy the laws of physics. This jet of particles streaming out from one of the galaxies doesn't follow the straight, predictable path we'd expect. Instead, it twists and bends as if sculpted by an invisible hand. This bizarre distortion is a direct result of the immense gravitational forces unleashed by the collision of the MICE galaxies. The warped jet originates from the vicinity of a supermassive black hole where particles are accelerated to nearly the speed of light. Under normal circumstances, such jets would shoot out in a straight line, but here, the chaotic gravitational environment warps their trajectory. The collision has created a maelstrom of gravitational forces, tugging and twisting the jet into its unusual shape. This bending effect is a vivid demonstration of how gravity can manipulate even the most energetic phenomena in the universe. What makes the warped jet particularly striking is its appearance. Unlike the sharp, linear jets seen in other galaxies, this one resembles a cosmic ribbon, curling and looping through space. Its twisted form is a testament to the sheer power of the galactic collision, which has reshaped not just the galaxies themselves, but also the high-energy processes occurring within them. The jet's distorted path also provides clues about the distribution of matter and the intensity of gravitational fields in this turbulent region. Scientists believe that studying the warped jet could offer new insights into the behavior of black holes and the dynamics of galactic collisions. Its unusual shape challenges existing models of how jets interact with their surroundings, prompting researchers to refine their theories. Could this be a common feature in colliding galaxies, or is it unique to the MICE galaxies? The answers lie in further observations and simulations, which may reveal even more about the forces at play in this cosmic dance. As we marvel at the warped jet's contorted form, we're reminded of the universe's capacity to surprise and challenge our understanding. This twisted stream of particles is not just a curiosity, it's a window into the complex interplay of gravity, energy, and matter in one of the most dramatic events in the cosmos. With a warped jet now in focus, we prepare to explore the cosmic veil, a delicate structure that obscures part of the galaxies and holds secrets of its own. Now turning our attention to the cosmic veil, we encounter a delicate yet enigmatic structure that drapes across the MICE galaxies like a translucent curtain. This thin veil of gas and dust, though seemingly fragile, plays a crucial role in shaping our understanding of these colliding galaxies. Its ethereal appearance belies the complex processes that brought it into existence, offering a glimpse into the intricate dance of matter and energy in this cosmic collision. The cosmic veil formed as a result of the immense tidal forces generated by the galaxy's collision. As the two galaxies pulled and stretched each other, vast clouds of gas and dust were ejected into the surrounding space. Over time, these clouds settled into a thin, wispy layer that now obscures parts of the galaxies from our view. This veil is not just a passive observer, it actively interacts with the light and radiation passing through it, scattering and absorbing certain wavelengths, which makes it a fascinating subject for astronomers. One of the most striking features of the cosmic veil is its delicate structure. Unlike the dense, opaque clouds often seen in other galaxies, this veil is almost ghostly, with intricate patterns that resemble fine lace. These patterns are shaped by the interplay of radiation from nearby stars and the gravitational forces of the galaxies themselves. The veil's transparency allows us to peer through it in some regions, revealing glimpses of the galaxy's cores and the chaotic activity within. However, the cosmic veil also poses challenges for astronomers. Its presence complicates observations of the galaxies as it filters and distorts the light coming from behind it. This filtering effect can make it difficult to study the underlying structures and processes, such as star formation or the behavior of the supermassive black holes. Yet, these challenges also present opportunities. By analyzing how the veil interacts with light, scientists can learn more about its composition, density, and the conditions that shaped it. The cosmic veil is more than just an obstacle, it's a treasure trove of information. Its formation and evolution provide clues about the history of the MICE galaxy's collision and the forces at work in this dynamic environment. As we continue to study this delicate structure, we uncover new insights into the life cycle of galaxies and the role of gas and dust in shaping the universe. With the cosmic veil now in focus, we prepare to explore the starburst ring, a region of intense star formation that illuminates the galaxies with its fiery glow. This next chapter promises to reveal even more about the transformative power of galactic collisions. Now shifting our gaze to the starburst ring, we uncover a dazzling spectacle of cosmic creation. This ring-shaped region, glowing with the fiery birth of countless stars, stands as a testament to the transformative power of galactic collisions. Nestled within the MICE galaxies, the starburst ring is a vibrant hub of activity where the chaos of the collision has ignited a frenzy of star formation unlike anything seen in more tranquil galaxies. The formation of the starburst ring is a direct result of the immense forces unleashed during the collision of the MICE galaxies. As the two galaxies spiraled toward each other, their gravitational interactions compressed vast clouds of gas and dust, triggering a chain reaction of starbirth. These compressed regions, now glowing brightly, form the ring-like structure that encircles part of the galaxies. The intense pressure and heat within these clouds cause them to collapse under their own gravity, giving rise to new stars at an astonishing rate. What makes the starburst ring particularly fascinating is its role in galactic evolution. The rapid formation of stars within this ring provides a snapshot of how galaxies can transform under extreme conditions. The collision not only fuels the creation of new stars but also redistributes material across the galaxies, shaping their future structure and composition. This process offers valuable insights into how galaxies grow and evolve over billions of years. The stars born within the starburst ring are not ordinary, they are massive, hot, and incredibly luminous. These young stars emit intense radiation, which in turn heats the surrounding gas and dust, creating a glowing halo around the ring. This radiation also drives powerful stellar winds, carving out cavities and shaping the environment around them. Over time, these stars will explode as supernova, scattering heavy elements into space and enriching the galaxies with the building blocks for future generations of stars and planets. Studying the starburst ring also helps astronomers understand the conditions necessary for such intense star formation. By analyzing the ring's structure, composition, and the types of stars it produces, scientists can piece together the sequence of events that led to its creation. This knowledge not only sheds light on the MICE galaxies, but also provides a framework for understanding similar phenomena in other colliding galaxies across the universe. As we marvel at the brilliance of the starburst ring, we are reminded of the dynamic and ever-changing nature of the cosmos. This ring of fire, born from chaos, illuminates the path to understanding how galaxies are shaped by their most dramatic encounters. With this fiery spectacle now in view, we prepare to explore the phantom disk, a faint and ghostly structure that holds its own secrets about the MICE galaxy's turbulent past. Now turning to the phantom disk, we encounter a hauntingly beautiful structure that seems to drift like a ghost within the MICE galaxies. This faint disk of stars and gas, barely visible against the backdrop of the colliding galaxies, holds clues to a dramatic cosmic event: the absorption of a smaller galaxy. The phantom disk is a remnant of this ancient encounter, a ghostly echo of a galaxy that once existed independently but has now been consumed by the larger galaxies. The formation of the phantom disk is a story of galactic cannibalism. As the MICE galaxies collided, their immense gravitational pull began to tear apart a smaller, neighboring galaxy. Over time, the stars and gas from this smaller galaxy were stretched and pulled into a disk-like shape, orbiting the larger galaxies. This process, known as tidal disruption, is a common occurrence in galactic collisions, but the phantom disk stands out for its faint, almost ethereal appearance. Its ghostly glow is a testament to the delicate balance between destruction and creation in the universe. What makes the phantom disk particularly intriguing is its composition. Unlike the bright, dense regions of star formation we've seen in other parts of the MICE galaxies, this disk is composed of older stars and diffuse gas. These remnants are the last traces of the smaller galaxy, now scattered and fading as they merge with the larger galaxies. The disk's faintness suggests that it has been stripped of much of its original material, leaving behind only a wispy outline of its former self. Astronomers believe that studying the phantom disk can provide valuable insights into the process of galactic mergers. By analyzing its structure and the motion of its stars, scientists can piece together the history of the smaller galaxy and understand how it was absorbed. This information helps us better grasp the mechanisms of galactic evolution and the role that collisions play in shaping the universe. The phantom disk serves as a cosmic fossil, preserving the story of a galaxy that no longer exists in its original form. The ghostly appearance of the phantom disk also raises questions about the fate of its stars. Over time, these stars will likely be fully integrated into the larger galaxies, losing their identity as part of the disk. Some may be flung into the outer reaches of the galaxies, while others could be drawn toward the galactic centers, where they might contribute to the growth of supermassive black holes. This gradual assimilation highlights the dynamic and ever-changing nature of galaxies, where even the faintest structures play a role in shaping the cosmos. As we contemplate the phantom disk, we are reminded of the delicate interplay between destruction and creation in the universe. This ghostly structure, born from the remnants of a smaller galaxy, offers a glimpse into the complex processes that drive galactic evolution. With this ethereal disk now in view, we prepare to explore the cosmic spire, a towering structure that stands as a monument to the forces unleashed by the collision of the MICE galaxies. Now shifting our gaze to the cosmic spire, we encounter one of the most visually stunning structures within the MICE galaxies. This towering spire of gas and dust rises like a cosmic skyscraper, stretching across vast distances and dominating the surrounding landscape. Its sheer size and dramatic shape make it a standout feature in this already extraordinary galactic collision. The formation of the cosmic spire is a story of immense forces at work. As the MICE galaxies collided, shockwaves rippled through the interstellar medium, compressing gas and dust into dense, towering structures. These shockwaves, combined with the powerful gravitational forces of the colliding galaxies, likely played a key role in shaping the spire. Some astronomers suggest that magnetic fields may also have contributed, channeling the gas and dust into this striking vertical formation. The result is a structure that appears almost sculpted, as if nature itself carved a monument to the chaos of galactic collisions. What makes the cosmic spire truly remarkable is its appearance. The spire glows faintly, illuminated by the light of nearby stars and the energy of the collision itself. Its surface is marked by intricate patterns of gas and dust, creating a textured, almost ethereal look. At its base, the spire blends into the surrounding galactic material, while its peak seems to pierce the void of space, reaching toward the unknown. This contrast between the spire's solid, towering form and its delicate, glowing details makes it a breathtaking sight. The cosmic spire also serves as a natural laboratory for studying the effects of galactic collisions. Within its structure, astronomers have detected regions of intense star formation, where the compressed gas and dust are giving birth to new stars. These stellar nurseries are hidden within the spire's folds, adding another layer of complexity to its story. The spire's towering height and dense composition suggest that it may continue to evolve, potentially collapsing further to form even more stars or even a massive star cluster. As we marvel at the cosmic spire, we are reminded of the incredible forces that shape our universe. This towering structure, born from the chaos of a galactic collision, stands as a testament to the interplay of destruction and creation. Its striking appearance not only captivates the imagination, but also provides valuable insights into the processes that drive the evolution of galaxies. With the cosmic spire now in view, we prepare to explore the radio arc, a mysterious structure that reveals yet another layer of the MICE galaxy's cosmic drama. Now turning our attention to the radio arc, we uncover another fascinating feature within the MICE galaxies. This arc-shaped structure, glowing with radio waves, stands out as a striking example of the dynamic processes at play in this galactic collision. The radio arc is not just a visual marvel, but also a key to understanding the powerful forces unleashed by the supermassive black hole at the heart of one of the galaxies. The formation of the radio arc is deeply tied to the activity of the supermassive black hole. As matter spirals into the black hole, it generates immense energy, some of which is ejected in the form of powerful jets. These jets, composed of charged particles moving at nearly the speed of light, interact with the surrounding gas and magnetic fields, creating the arc-shaped structure we observe. The radio arc is essentially a snapshot of this interaction, a glowing trail left behind by the black hole's energetic outbursts. What makes the radio arc particularly intriguing is its unique emissions. Unlike visible light, radio waves can penetrate the dense clouds of gas and dust that often obscure other features in the galaxies. This allows astronomers to study the arc in remarkable detail, revealing its intricate structure and the processes that shaped it. The arc's emissions are not uniform. Instead, they vary in intensity, hinting at the complex interplay between the black hole's jets and the surrounding material. The radio arc also provides valuable insights into the broader effects of the galactic collision. As the two galaxies interact, their gravitational forces and magnetic fields influence the behavior of the black hole's jets, bending and shaping them into the arc we see today. This bending effect, known as relativistic beaming, is a direct result of the extreme conditions created by the collision. It's a vivid reminder of how interconnected these cosmic events are, with each element influencing and reshaping the others. As we study the radio arc, we gain a deeper appreciation for the role of supermassive black holes in galactic evolution. These cosmic powerhouses not only shape their immediate surroundings, but also leave lasting imprints on the larger structure of the galaxies. The radio arc, with its glowing emissions and dramatic shape, serves as a testament to the enduring impact of these enigmatic objects. With the radio arc now in focus, we prepare to explore the ghostly cluster, a faint yet intriguing collection of stars that holds its own secrets within the MICE galaxies. Now shifting our gaze to the ghostly cluster, we encounter a faint yet mesmerizing collection of stars nestled within the MICE galaxies. This ethereal grouping of stars, barely visible against the backdrop of the colliding galaxies, holds clues to one of the most fundamental processes in the universe, galactic mergers. The ghostly cluster is believed to be the remnants of a smaller galaxy that was absorbed by one of the larger galaxies in this cosmic collision. As the smaller galaxy was torn apart by tidal forces, its stars were scattered, leaving behind this faint, ghostly trace. The formation of the ghostly cluster offers a fascinating glimpse into the mechanics of galactic cannibalism. When a smaller galaxy is absorbed by a larger one, its stars are not immediately assimilated. Instead, they are stretched into long streams or dispersed into clusters like the one we see here. Over time, these stars may eventually merge with the larger galaxy, but for now, they remain as a haunting reminder of the smaller galaxy's existence. The ghostly cluster is a snapshot of this process, capturing the moment when a galaxy is in the throes of being consumed. What makes this cluster particularly significant is its role in helping astronomers understand the dynamics of galactic mergers. By studying the distribution and motion of its stars, scientists can piece together the history of the collision. For instance, the faintness of the cluster suggests that the smaller galaxy was likely low in mass, making it more susceptible to being torn apart. Additionally, the cluster's position within the larger galaxy provides insights into how tidal forces operate during such mergers, shaping the final structure of the surviving galaxy. The ghostly cluster also serves as a reminder of the interconnected nature of the universe. Galactic mergers are not just destructive events, they are also creative forces that drive the evolution of galaxies. The stars from the smaller galaxy may eventually contribute to the formation of new structures within the larger galaxy, such as star clusters or even new spiral arms. In this way, the ghostly cluster is not just a relic of the past, but also a harbinger of future galactic evolution. As we reflect on the ghostly cluster, we are reminded of the delicate balance between destruction and creation in the cosmos. This faint cluster of stars, though barely visible, tells a profound story of galactic transformation. With this in mind, we now turn our attention to the cosmic knot, a dense and compact structure that offers yet another intriguing piece of the MICE Galaxies puzzle. Now turning to the cosmic knot, we find ourselves staring at one of the most intriguing structures within the MICE Galaxies. This dense, tightly packed knot of gas and stars stands out as a beacon of cosmic activity, its compact form hinting at the immense forces at play during the galaxy's collision. The cosmic knot is not just a random clump of material, it's a potential cradle for new star formation, a place where the raw ingredients of the universe come together under the influence of gravity and pressure. The formation of the cosmic knot is a story of chaos and creation. As the two galaxies collide, their gas clouds are compressed, creating regions of intense density. These regions, like the cosmic knot, become hotspots for gravitational collapse. Over time, the gas and dust within the knot may begin to coalesce, forming the seeds of new stars. What makes this knot particularly fascinating is its compactness. Unlike the sprawling structures we often see in galaxies, the cosmic knot is a concentrated mass, suggesting that it may eventually evolve into a dense star cluster, perhaps even a globular cluster, one of the most ancient and tightly bound collections of stars in the universe. The potential for star formation within the cosmic knot is immense. As the gas within the knot continues to collapse under its own gravity, it heats up, reaching temperatures that can ignite nuclear fusion. This process, the birth of stars, is one of the most fundamental and awe-inspiring events in the cosmos. The cosmic knot, with its dense core and swirling outer layers, is a prime candidate for such stellar nurseries. In fact, astronomers have observed similar knots in other colliding galaxies, many of which have gone on to form spectacular star clusters. But the cosmic knot is more than just a site of potential star formation. Its compact structure also provides valuable insights into the dynamics of galactic collisions. The knot's density and shape reveal how gas behaves under extreme conditions, offering clues about the forces that shape galaxies during mergers. By studying the cosmic knot, scientists can better understand how these collisions trigger star formation and influence the evolution of galaxies over billions of years. As we marvel at the cosmic knot, we are reminded of the incredible complexity and beauty of the universe. This dense, glowing structure is a testament to the transformative power of galactic collisions, where destruction gives way to creation. With this in mind, we now shift our focus to the Phantom Nebula, a mysterious and elusive object that adds yet another layer of intrigue to the MICE Galaxies story. Now, as we turn our gaze to the Phantom Nebula, we encounter one of the most enigmatic objects in the MICE Galaxies. This nebula, with its ghostly presence, seems to play a cosmic game of hide and seek, vanishing and reappearing in observations over time. Its elusive nature has left astronomers both puzzled and fascinated, sparking a quest to uncover the secrets behind its mysterious behavior. The Phantom Nebula's vanishing act could be explained by several intriguing possibilities. One leading theory points to variable illumination, where changes in the brightness of nearby stars or other light sources cause the nebula to fade in and out of view. Imagine a cosmic spotlight shifting its focus, sometimes illuminating the nebula and at other times leaving it shrouded in darkness. This variability could be due to the erratic behavior of young, massive stars within the galaxies, whose intense radiation can fluctuate dramatically over time. Another compelling explanation involves gravitational lensing, a phenomenon where the immense gravity of a massive object, like a black hole or a dense cluster of stars, bends and distorts the light from objects behind it. In the case of the Phantom Nebula, this lensing effect might magnify or obscure its light, creating the illusion that it disappears and reappears. It's as if the universe itself is playing tricks on us, using its own gravitational forces to hide and reveal this celestial wonder. The Phantom Nebula's behavior also raises questions about its composition and structure. Could it be a transient feature, a temporary gathering of gas and dust that is slowly dissipating? Or is it a more stable structure, its visibility simply affected by external factors? These questions highlight the challenges of studying such dynamic and unpredictable objects, reminding us that the universe is full of surprises. What makes the Phantom Nebula particularly captivating is its ability to challenge our understanding of cosmic phenomena. It forces us to consider the interplay of light, gravity, and time in ways that stretch our imagination. By studying this elusive nebula, scientists hope to gain deeper insights into the mechanisms that govern the visibility and behavior of celestial objects, shedding light on the broader mysteries of the cosmos. As we ponder the Phantom Nebula's ghostly dance, we are reminded of the ever-changing nature of the universe. This mysterious object, with its fleeting appearances, invites us to look closer, to question, and to marvel at the wonders that lie hidden in the depths of space. With this in mind, we now move forward to explore the warped jet, another extraordinary feature shaped by the cosmic forces at play in the MICE galaxies. Now shifting our focus to the warped jet, we encounter yet another marvel shaped by the chaotic forces of the MICE galaxies. This jet of particles, unlike the straight, narrow streams we often associate with such phenomena, appears bent and twisted as if sculpted by an unseen cosmic hand. Its unusual shape is a direct result of the immense gravitational forces unleashed during the collision of these two galaxies, creating a spectacle that defies our expectations. The warped jet originates from the vicinity of a supermassive black hole, where particles are accelerated to nearly the speed of light and ejected into space. Normally, these jets shoot out in straight lines, but in the MICE galaxies, the intense gravitational pull from the collision has warped their trajectory. Imagine a river flowing smoothly until it encounters a powerful whirlpool, bending its course in unpredictable ways. Similarly, the gravitational forces from the merging galaxies have twisted this jet into a mesmerizing, contorted shape. What makes the warped jet particularly fascinating is its ability to reveal the invisible forces at play. The bending and twisting of the jet provide astronomers with a unique opportunity to study the distribution of mass and gravity within the galaxies. By analyzing its shape, scientists can map the gravitational fields that influenced its path, offering insights into the complex dynamics of galactic collisions. It's like using a cosmic compass to navigate the unseen forces shaping the universe. The warped jet also challenges our understanding of how such structures behave under extreme conditions. Its unusual appearance raises questions about the stability and longevity of these jets in chaotic environments. Could the distortion eventually cause the jet to dissipate, or will it continue to flow, adapting to the ever-changing gravitational landscape? These questions highlight the dynamic nature of the MICE galaxies and the ongoing interplay between matter and gravity. As we marvel at the warped jet's contorted form, we are reminded of the immense power of galactic collisions. This twisted stream of particles is not just a visual spectacle but a testament to the forces that shape the cosmos. With this in mind, we now turn our attention to the cosmic veil, a delicate structure that further illustrates the intricate beauty of the MICE galaxies. Now turning our gaze to the cosmic veil, we encounter a delicate and ethereal structure that drapes across the MICE galaxies like a translucent curtain. This thin veil of gas and dust, though seemingly fragile, plays a crucial role in shaping our understanding of these colliding galaxies. Its wispy appearance belies the complex processes that brought it into existence, offering a glimpse into the intricate dance of matter and energy in the cosmos. The cosmic veil likely formed as a result of the immense tidal forces generated by the collision of the two galaxies. As they grazed past each other, vast clouds of gas and dust were pulled outward, stretched into long, thin filaments that now hang in space like a cosmic tapestry. These filaments, illuminated by the light of nearby stars, create a hauntingly beautiful effect, obscuring parts of the galaxies while revealing the delicate interplay of forces at work. What makes the cosmic veil particularly intriguing is its impact on observations. The veil acts as a natural filter, dimming the light from stars and other objects behind it. This can make it challenging for astronomers to study the regions it covers, but it also provides valuable information about the composition and density of the material within the veil itself. By analyzing how light passes through or is absorbed by the veil, scientists can piece together clues about the history and evolution of the MICE galaxies. The delicate structure of the cosmic veil also serves as a reminder of the transient nature of galactic collisions. Over time, the veil may dissipate, its material either falling back into the galaxies or being swept away by stellar winds. Yet, for now, it stands as a testament to the beauty and complexity of the universe, a fleeting masterpiece crafted by the forces of gravity and motion. As we marvel at the cosmic veil's intricate patterns, we are reminded of the countless mysteries still waiting to be uncovered in the MICE galaxies. With this in mind, we now shift our focus to the starburst ring, a region of intense star formation that further highlights the dynamic nature of these colliding galaxies. Now shifting our focus to the starburst ring, we encounter a dazzling spectacle of cosmic creation. This ring-shaped region, glowing with the light of countless newborn stars, is one of the most striking features of the MICE galaxies. Its brilliance is a direct result of the ongoing collision between the two galaxies, which has unleashed a torrent of star formation unlike anything seen in more tranquil regions of the universe. The starburst ring, formed as shockwaves from the galactic collision, compressed vast clouds of gas and dust, igniting a frenzy of starbirth. These shockwaves, rippling through the galaxies, triggered the collapse of these clouds, causing them to fragment and coalesce into new stars. The result is a luminous ring, teeming with young, hot stars that shine with an intensity that outshines even the oldest stellar populations in the galaxies. What makes the starburst ring particularly fascinating is its role in galactic evolution. The intense star formation within the ring not only produces new stars but also enriches the surrounding environment with heavy elements forged in the heart of these stellar furnaces. Over time, these elements will be incorporated into future generations of stars and planets, shaping the chemical makeup of the galaxies for billions of years to come. The ring also serves as a laboratory for studying the conditions necessary for star formation. By observing the processes at work within the starburst ring, astronomers can gain insights into how galaxies evolve and how collisions influence their development. The sheer scale of the star formation here is a testament to the transformative power of galactic mergers, revealing how such events can reshape entire galaxies in profound and lasting ways. As we marvel at the starburst ring's radiant beauty, we are reminded of the dynamic and ever-changing nature of the universe. This ring of light is not just a fleeting phenomenon, but a key piece of the puzzle in understanding how galaxies grow, evolve, and interact over cosmic time. With this in mind, we now turn our attention to the phantom disk, a ghostly remnant of a smaller galaxy absorbed by the MICE galaxies, offering yet another glimpse into the complex history of these colliding giants. Now turning to the phantom disk, we uncover a hauntingly beautiful structure hidden within the MICE galaxies. This faint disk of stars and gas, barely visible against the backdrop of the colliding galaxies, is believed to be the ghostly remnant of a smaller galaxy that was absorbed during the merger. Its ethereal glow and delicate structure offer a glimpse into the violent yet transformative processes that shape galactic evolution. The phantom disk likely formed as the gravitational forces of the MICE galaxies tore apart a smaller, neighboring galaxy. As the smaller galaxy was pulled into the collision, its stars and gas were stretched into a thin, disk-like structure, now faintly visible amidst the chaos. This process, known as galactic cannibalism, is a common occurrence in the universe where larger galaxies consume smaller ones, incorporating their material into their own structure. What makes the phantom disk particularly intriguing is its ghostly appearance. Unlike the bright, vibrant regions of star formation we've explored earlier, this disk is dim and diffuse, almost like a shadow of its former self. Yet, within this faint glow lies a wealth of information about the history of the MICE galaxies. By studying the composition and motion of the stars and gas within the disk, astronomers can piece together the story of the smaller galaxy's demise and its contribution to the larger system. The phantom disk also serves as a reminder of the dynamic nature of galactic interactions. While the collision of the MICE galaxies has created dazzling features like the starburst ring and the cosmic ribbon, it has also left behind quieter, more subtle remnants like this disk. These structures, though less conspicuous, are just as important in understanding the full picture of galactic evolution. As we examine the phantom disk, we are reminded that even in the vastness of space, nothing is truly lost. The stars and gas of the absorbed galaxy live on, woven into the fabric of the MICE galaxies, contributing to their growth and transformation. With this in mind, we now shift our gaze to the cosmic spire, a towering structure of gas and dust that stands as a testament to the immense forces at play in this cosmic collision. Now shifting our focus to the cosmic spire, we encounter one of the most visually striking structures within the MICE galaxies. This towering spire of gas and dust rises like a celestial skyscraper, stretching across vast distances and dominating the surrounding landscape of the colliding galaxies. Its sheer size and dramatic appearance make it a standout feature, drawing the eye and sparking curiosity about its origins. The cosmic spire is believed to have formed as a result of the immense shock waves generated by the collision of the two galaxies. As the galaxies slammed into each other, the resulting tidal forces and gravitational interactions compressed vast clouds of gas and dust, pushing them into towering columns. These shockwaves acted like cosmic sculptors, carving out the spire's intricate shape and giving it its towering, needle-like form. Alternatively, some astronomers suggest that the spire may have been shaped by the intense gravitational forces at play, which pulled and stretched the material into its current configuration. What makes the cosmic spire truly remarkable is its striking appearance. The spire glows faintly with the light of embedded stars and the reflection of nearby starlight off its dusty surface. Its edges are sharp and well-defined, contrasting with the chaotic swirls of gas and dust that surround it. At its peak, the spire seems to pierce the darkness of space, creating a dramatic visual that captures the imagination. This structure is not just a beautiful sight, it also holds important clues about the processes shaping the MICE galaxies. The spire's composition and structure can reveal details about the forces at work during the collision, such as the strength of the shock waves and the distribution of material within the galaxies. Additionally, the spire may serve as a nursery for new stars, as the dense gas and dust within it could collapse under gravity to form stellar systems. As we marvel at the cosmic spire, we are reminded of the incredible forces that shape our universe. From the violent collisions of galaxies to the delicate interplay of gravity and shock waves, these processes create structures that are both awe-inspiring and scientifically significant. With this in mind, we now turn our attention to the radio arc, another fascinating feature born from the chaos of the MICE galaxies' collision. Now shifting our gaze to the radio arc, we uncover yet another extraordinary feature within the MICE galaxies. This arc-shaped structure, glowing with intense radio emissions, stands out as a testament to the powerful forces at play during the galactic collision. Stretching across the sky, the radio arc is not just a visual marvel, but also a key to understanding the dynamic processes shaping these galaxies. The radio arc is closely linked to the supermassive black hole at the heart of one of the colliding galaxies. As the black hole devours surrounding matter, it generates immense energy, some of which is channeled into powerful jets of particles. These jets, traveling at nearly the speed of light, interact with the surrounding gas and magnetic fields, creating the arc-shaped structure we observe. The result is a glowing ribbon of radio waves that traces the path of these energetic particles, illuminating the otherwise invisible forces at work. What makes the radio arc particularly fascinating is its formation. As the galaxies collided, the shock waves and tidal forces compressed and heated the gas, creating the perfect conditions for the black hole's jets to carve out this unique structure. The arc's curvature is a direct result of the interplay between the jets and the magnetic fields threading through the galaxies. This interaction not only shapes the arc but also accelerates particles to extreme energies, causing them to emit the radio waves that make the structure visible to astronomers. The radio arc's emissions provide valuable insights into the behavior of supermassive black holes and their impact on their surroundings. By studying the arc, scientists can learn more about how black holes influence galactic evolution, from triggering star formation to redistributing matter across vast distances. Additionally, the arc's unique shape and emissions offer clues about the strength and orientation of the magnetic fields within the MICE galaxies, shedding light on the complex physics of galactic collisions. As we explore the radio arc, we are reminded of the intricate connections between the largest and smallest scales in the universe. From the immense power of supermassive black holes to the delicate interplay of magnetic fields, these phenomena create structures that are both beautiful and scientifically significant. With this in mind, we now turn our attention to the ghostly cluster, another mysterious feature born from the chaos of the MICE galaxies collision. Now turning our attention to the ghostly cluster, we encounter a faint yet captivating group of stars nestled within the MICE galaxies. This elusive cluster, barely visible against the backdrop of the colliding galaxies, holds secrets about the cosmic dance of galactic mergers. Its faint glow suggests it may be the remnants of a smaller galaxy, slowly being absorbed by one of the larger galaxies in this dramatic collision. The formation of the ghostly cluster is a story of cosmic cannibalism. As the MICE galaxies collide, their immense gravitational forces pull in smaller galaxies that happen to be nearby. These smaller galaxies are torn apart, their stars scattered and redistributed. Over time, some of these stars clump together, forming clusters like the one we see here. The ghostly cluster is likely one such survivor, a relic of a galaxy that once existed independently but is now being assimilated into the larger structure. What makes this cluster particularly intriguing is its faintness. Unlike the bright, densely packed star clusters often seen in galaxies, the ghostly cluster appears dim and diffuse. This suggests that its stars are spread out over a larger area, possibly due to the tidal forces exerted during the merger. These forces stretch and distort the cluster, thinning out its stars and giving it its ghostly appearance. Yet, despite its faintness, the cluster remains intact, a testament to the resilience of stellar systems even in the face of such violent events. The ghostly cluster is more than just a cosmic curiosity. It plays a crucial role in helping astronomers understand galactic mergers. By studying its structure and composition, scientists can piece together the history of the collision and the fate of smaller galaxies caught in the gravitational crossfire. The cluster's stars, once part of a separate galaxy, now mingle with those of the larger galaxies, providing clues about how galaxies grow and evolve over time. This process, known as hierarchical merging, is a fundamental aspect of galactic evolution, and the ghostly cluster offers a rare glimpse into its mechanics. As we examine this faint cluster, we are reminded of the delicate balance between destruction and creation in the universe. The absorption of smaller galaxies may seem destructive, but it also fuels the growth of larger galaxies, shaping the cosmos as we know it. With this in mind, we now shift our focus to the cosmic knot, another fascinating structure born from the chaos of the MICE galaxies collision. Now shifting our gaze to the cosmic knot, we encounter a tightly packed, dense region of gas and stars that stands out amidst the chaos of the MICE galaxies. This compact structure, resembling a tangled web of cosmic material, is a striking example of how the collision between these galaxies can create such intricate and fascinating formations. The cosmic knot is not just a random clump of matter. It represents a critical stage in the process of star formation, offering a glimpse into how new stellar systems emerge from the turmoil of galactic interactions. The formation of the cosmic knot is likely tied to the immense gravitational forces at play during the collision. As the two galaxies pull and twist each other, pockets of gas and dust are compressed, creating regions of high density. These dense areas can collapse under their own gravity, forming knots of material that may eventually give birth to new stars. The cosmic knot we see here is one such region where the pressure and temperature are just right for star formation to begin. Its compact structure suggests that it is in the early stages of this process, with the potential to evolve into a fully fledged star cluster in the future. What makes the cosmic knot particularly intriguing is its potential to become a nursery for new stars. Within its dense core, gas and dust are swirling and colliding, creating the perfect conditions for protostars to form. Over time, these protostars will ignite, lighting up the knot and transforming it into a vibrant cluster of young stars. This process is a key part of galactic evolution, as it replenishes the stellar population and shapes the structure of the galaxies involved. The cosmic knot, therefore, is not just a static feature. It is a dynamic region where the future of the MICE galaxies is being forged. The compact nature of the cosmic knot also provides valuable insights into the mechanics of star formation. By studying its structure and composition, astronomers can better understand how gas and dust behave under extreme conditions and how these conditions lead to the birth of new stars. The knot's dense core, with its swirling gas and potential protostars, serves as a natural laboratory for exploring the early stages of stellar evolution. This makes it a key area of interest for scientists seeking to unravel the mysteries of how stars and galaxies form and evolve. As we marvel at the cosmic knot, we are reminded of the incredible complexity and beauty of the universe. This dense, compact structure is a testament to the transformative power of galactic collisions, where destruction and creation go hand in hand. With this in mind, we now turn our attention to the Phantom Nebula, another enigmatic feature of the MICE galaxies that challenges our understanding of the cosmos. Now turning our attention to the Phantom Nebula, we encounter one of the most baffling phenomena in the MICE galaxies. This mysterious nebula has been observed to vanish and reappear, leaving astronomers both intrigued and puzzled. Its ghostly behavior challenges our understanding of cosmic structures and raises questions about the forces at play in this colliding galaxy system. One possible explanation for the Phantom Nebula's elusive nature is variable illumination. The nebula's glow could be influenced by nearby stars or other light sources that fluctuate in brightness. When these sources dim, the nebula may appear to vanish, only to reappear when the light intensifies again. This interplay of light and shadow creates an illusion of disappearance, making the nebula seem like a phantom in the vastness of space. Another compelling theory involves gravitational lensing, a phenomenon where the gravity of massive objects bends and distorts light from background sources. In the case of the Phantom Nebula, the intense gravitational forces generated by the colliding galaxies could be acting as a cosmic lens. As the galaxies move and shift, the lensing effect might temporarily obscure the nebula, causing it to vanish from view. When the alignment changes, the nebula reappears as if emerging from a cosmic veil. The Phantom Nebula's behavior also raises questions about its composition and structure. Could it be a transient feature formed and dissolved by the turbulent forces of the galactic collision? Or is it a more stable structure that only appears to vanish due to external factors? These questions highlight the complexity of studying such dynamic environments, where the interplay of light, gravity, and motion creates phenomena that defy easy explanation. As we ponder the mysteries of the Phantom Nebula, we are reminded of the ever-changing nature of the universe. This enigmatic feature serves as a reminder that even in the vastness of space, there are still phenomena that challenge our understanding and spark our curiosity. With this in mind, we now shift our focus to the warped jet, another extraordinary feature of the MICE galaxies that continues to captivate astronomers and stargazers alike. Now shifting our gaze to the warped jet, we encounter yet another marvel in the MICE galaxies that defies conventional expectations. This jet of particles emanating from one of the galaxies appears strikingly bent and twisted, as if sculpted by an unseen cosmic hand. Its unusual shape has captivated astronomers, offering a glimpse into the powerful forces at play during the collision of these two galaxies. The warped jet's distorted appearance is a direct result of the immense gravitational forces generated by the galactic collision. As the two galaxies interact, their gravitational fields create a chaotic environment, warping the paths of nearby objects. The jet, which originates from a supermassive black hole at the heart of one galaxy, is caught in this gravitational tug-of-war. The intense pull from the neighboring galaxy bends the jet, causing it to twist and curve in ways that challenge our understanding of such phenomena. What makes the warped jet particularly fascinating is its dynamic nature. Unlike the steady, straight jets often observed in isolated galaxies, this jet's path is constantly shifting. As the galaxies continue to collide and their gravitational fields evolve, the jet's trajectory changes, creating a mesmerizing display of cosmic motion. This ever-changing appearance provides astronomers with a unique opportunity to study the effects of gravitational forces in real time. The warped jet also raises intriguing questions about the nature of particle jets in colliding galaxies. Could this bending and twisting be a common feature in such environments, or is it a rare occurrence specific to the MICE galaxies? By studying this phenomenon, scientists hope to gain deeper insights into how galactic collisions influence the behavior of supermassive black holes and their associated jets. As we marvel at the warped jet's unusual appearance, we are reminded of the intricate interplay of forces that shape our universe. This twisted stream of particles serves as a vivid reminder of the power and complexity of galactic collisions, offering a window into the dynamic processes that drive cosmic evolution. With this in mind, we now turn our attention to the final object in our exploration of the MICE galaxies, the cosmic veil, a delicate and mysterious feature that continues to intrigue astronomers worldwide. Now, as we approach the final object in our journey through the MICE galaxies, we encounter the cosmic veil, a delicate and enigmatic structure that seems to drape itself across the galaxies like a translucent curtain. This thin veil of gas and dust, though faint, plays a significant role in shaping our observations of these colliding galaxies. Its ethereal presence adds another layer of mystery to the already complex tapestry of the MICE galaxies. The cosmic veil is believed to have formed as a result of the ongoing collision between the two galaxies. As they interact, vast amounts of gas and dust are ejected into the surrounding space, creating this wispy, veil-like structure. Over time, these materials have spread out, forming a delicate barrier that partially obscures our view of the galaxies behind it. This process highlights the chaotic and dynamic nature of galactic collisions, where even the smallest particles can create large-scale structures. One of the most intriguing aspects of the cosmic veil is its impact on observations. The veil's presence makes it challenging for astronomers to study the regions of the galaxies it obscures. However, this challenge also presents an opportunity. By analyzing how light from the galaxies interacts with the veil, scientists can learn more about the composition and density of the gas and dust within it. This, in turn, provides valuable insights into the conditions present during the collision and the processes that drive galactic evolution. The cosmic veil's delicate structure is a testament to the intricate interplay of forces at work in the MICE galaxies. Its wispy tendrils and faint glow serve as a reminder of the beauty and complexity of the universe. As we conclude our exploration of the 50 strange objects in the MICE galaxies, the cosmic veil stands as a fitting final chapter, encapsulating the wonder and mystery that define these colliding galaxies. With this, we wrap up our journey through the MICE galaxies, having uncovered some of the most bizarre and fascinating objects in the universe. Each discovery has deepened our understanding of galactic collisions and the forces that shape our cosmos. If you've enjoyed this exploration, don't forget to like, share, and subscribe for more cosmic mysteries. Until next time, keep looking up and wondering at the vast, incredible universe around us. As we bring our journey through the MICE galaxies to a close, it's worth reflecting on the incredible array of strange objects we've encountered. From the twin supermassive black holes at the heart of the collision to the delicate cosmic veil that drapes across the galaxies, each discovery has offered a unique glimpse into the chaotic and awe-inspiring processes that shape our universe. These 50 objects are not just curiosities, they are windows into the forces that drive galactic evolution, revealing how collisions, gravity, and cosmic interactions sculpt the cosmos on a grand scale. The MICE galaxies have shown us that even in chaos there is beauty and order. The luminous bridge connecting the galaxies, the ghostly nebula floating between them, and the warped disks of stars and gas all tell a story of transformation and renewal. These phenomena challenge our understanding of the universe, pushing us to ask new questions and seek deeper answers. What drives the formation of such intricate structures? How do these collisions influence the birth and death of stars? And what can they teach us about the fate of our own galaxy? As we wrap up this exploration, we invite you to share your thoughts and theories in the comments below. What did you find most fascinating about the MICE galaxies? Do you have your own ideas about the origins of these strange objects? Let's continue the conversation and unravel the mysteries of the cosmos together. If you've enjoyed this journey, don't forget to like, share, and subscribe for more deep dives into the wonders of space. There's so much more to discover, and we can't wait to explore it with you. Until next time, keep your eyes on the stars and your curiosity alive. The universe is full of surprises waiting to be uncovered.